Hi, welcome to another edition of Calculus 3. Today we are going to take a second look at double integrals and volume. So the topic gets gradually harder and harder. Let's go ahead and see if we can make sense of this very intuitive idea, but it requires quite a bit of attention. Okay, double integrals and volume. We have been talking about double integrals or iterated integrals before, and we have looked at it in the context of calculating volumes. Here we are just adopting a more advanced notation. We are going to see double integral on top of a region, which we typically call as R, and then we have a function of two variables, f of x and y, and here we have something called element of area. All of this is going to give volume of a certain region in space. Let's see what do each of these items mean. The region R is some region on the xy plane. So here I've colored it yellow, that's a region R. On top of a xy plane we have some surface which is given as z is equal to function of x and y. So height of the surface is z. For each point in the xy plane we have a height z, which is a function f of x and y. Element of area typically at this level is just dx dy, some little rectangle here. On top of that rectangle there is a height. That height is given by that function. So what's the meaning of this notation? The meaning is the following. If I take a little area here and multiply it by the height, I'm going to get the volume of a little pencil looking region of space here. Pencil looking because this base is small and it's kind of thin and long. Now if I take my region, cut it up into little cells like this, elements of area like dA, so that it covers my region. If I take each of them and multiply by the corresponding height, I'll get the volume of that little pencil, and if I add the volumes of all the pencils, I get the volume under this dome on top of this region. Okay, that's what is meant by a double integral. We want to practice how to calculate it first as a matter of approximation so that we know what is referring to, and then some calculus-based calculation for finding the exact values. Let's go ahead and remind ourselves again what is the meaning of this notation. There is quite a bit of algebra involved, but the most important thing here is to understand what is meant by that notation. So we have looked at this picture once before, but it's always a good idea to look at it again. So this is meant to convey that concept we were talking about. We have some function here. You can have any function, f of x and y, and then we have some region on the xy plane, which is this rectangle here. In this three-dimensional picture, perhaps it's not easy to see, but here is that rectangle in the xy plane. In general it can be any shape, but here to simplify things we're just looking at the rectangle. This rectangle you can go ahead and define where it starts and where it ends, and you can define how many grid points you want in either direction. So for example, if I start from -2.5 and I go to +2.5, and say my y minimum starts at -2 and this is 2, and suppose in the x direction I want 6 cells, and in the y direction I want 5 cells. So that's how I'm cutting up my my rectangle. Of course, this is reflected here. Each of these little pencils now is built on top of the corresponding cell on the XY plane. What we are supposed to do is to take the area of the base, multiply by the height. How do we get the height? Well, height comes from this formula. So we go on the cell, we, for example, find some point, typically just the center of that cell. So that center of the cell has an XY coordinate. We pick that, we plug it into our function that tells us how high the ceiling is at that point. We take that height, multiply by the area of the base, which is the area of one of these little cells. So that tells us the volume of the little pencil that is sitting on top of that cell. Then we go ahead, add up all these little volumes. That's what the double integral notation refers to. It's a summation. And then that is going to give us an approximate area. How do we improve our approximation? Well, cut more and more cells. The more cells you have, the more accurate your approximation is going to be. But then, of course, you are spending more time adding all these things up. So there is a trade-off. Somehow, the more you pay, the more you get. So let's go ahead and practice the simple concept first. The question is, what does this notation really mean? So the best idea there is to just start with a very simple example and do it in an approximate fashion. So suppose I want to calculate. So here I have my function f of x and y. Pick any function. Let's just make it easy so that you're not spending too much time on the arithmetic front. So the region R, let's take it to be the rectangle from 0 to 2 times 0 to 3. What does this mean? Simply it means interval from 0 to 2. So say this is 2, and well, 0 to 3 is 0 to 2. So this is the x and this is the y. Somehow we indicate that rectangle. So that's our function. And then we want to decide on our cells. Just to make the problem very simple at the beginning, we are going to have 2 cells in the x direction and 3 cells in the y direction, so that our numbers will be friendly. So of course this is going to be a very rough approximation because our cells are so big, but we said if you make it very crowded, then of course then you're going to spend more time calculating everything. So this is our region R. So all of this is the region R. Now what we do is that we pay attention to each of the cells in it. So for example, we pick this cell. In that cell, we want to find out the contribution to the volume from that cell. Well, we have to find some point here. Best option is just go at the center of this cell. Well, where is the center? Obviously here, half and a half. So the center is, let's write it here, 0.5, 0.5. That's the center of the cell. Well, this is my function. My function is z is equal to x squared y. Now my x was 0.5, my y was 0.5. So my z becomes simply, I just plug it here, 0.5 squared times another 0.5, and we calculate this thing. So in this case it becomes 1, 2, 5, for example. Okay, that is the height here. I have to multiply by the area of the base. Luckily the area of my base is a very nice number. It's just the area is just 1. And then I repeat this process for each of these cells that I have. So the next one, x is 1.5, the y is still 0.5, so z is going to be 1.5 squared times 0.5, and so 2.25, and then I guess 1.125 if I'm not mistaken. So at that point we need a calculator to do all of these things. Next we go to x 0.5, so this was 0.5 and 1.5. This is of course 0.5 and 1.5. I made a mistake here. This is 1.5. That's the problem with these problems. You have to be very meticulous with your numbers. It's a repetitive action, but you have to be careful not to misplace things. So this point is 0.5, and then the y is 1.5. Next point is going to be 1.5 and the 1.5. Next one, x is first one again 0.5, and then y of it is going to be 2.5. Next point here, it's going to be 1.5 and 2.5. So if you wish, you can make a table. You have x's, y's, and the z values. Z is coming from our function which was x squared y. Okay, so you have to calculate all 6 of these things. I am going to leave that to you. Then we have to multiply each of these things by area of the base. Area of the base, you can show it, for example, by delta A. Delta A refers to the area of our bases. In the simplest case, all the bases are the same. More complicated ones, more advanced versions, you can choose the base to be different shapes and different areas, different places. But in this simple case, area of the base is just number 1. Now what we are going to do is we are going to calculate the element of volume. Element of volume is going to be z times the element of area. So in that case, it's going to be 0, 1.25, 1.125, and the other 4 contributions here. And then when you add them up, this whatever number we get here is total or approximate total volume. So perhaps this is the most important engineering lesson here. The integration problems that we do tend to be very mathematical, and in real life we almost never find out functions that are so nice. But we typically deal with data. That is, we have these as numbers coming from some experiment or some measurements, and we multiply by the area of the base and add them up, and we calculate our total volume. So what the double integral of f dA means is that you do a summation by taking f calculated at some point in each of those cells. We multiply by the area of each of those cells, and then we add them up. Then we take a limit of all of these things as well. How do we take a limit? We have to make our rectangles, our cells, to be as small, to make them smaller and smaller. How do we measure that our rectangles are becoming small? The easiest way to do this thing is to measure the diagonal of this thing. So the diagonal of each of these rectangles are going to be considered, and then we define a partition. Partition simply refers to this cell. The size of the partition is going to be the largest diagonal. So the largest diagonal in our cells is going to be the size of the partition. Now, in our problems, all the cells are the same. They are all squares or rectangles, so all of their diameters are going to be the same, but in general they could be different. So we take the largest of all of these diagonals, and then we make sure that the largest of them that tends to 0. So that is how we take the limit. So at the limit that our grid becomes smaller and smaller to the point that the diagonal of all the cells are going towards 0, the limit of this sum is defined to be what the double integral is. Okay, so this is something similar to what you had in Calculus 1 with the so-called Riemann integral. Now, there are a couple of theorems in these sections referred to as Fubini's theorem, but I'm going to leave you to read that in the text itself, and we are going to go ahead and take a look at some example problems. So very similar to last time, here's a question we want to do. Find the double integral of a function where R is the region between between x is equal to radical y and x is equal to y over 2. F of x and y is x squared y squared. So these problems are a bit harder than the ones we had last time because we have to figure out exactly where we are doing all the integration. So in the previous set of problems, everything kind of spelled out in detail, but now we are picking it apart and putting everything together to figure out what the integral is. So a huge component of this is to figure out what the region is. So that requires our knowledge of Calculus 1. We have to be able to quickly figure out what kind of boundaries we are dealing with, where are the intersections, where do we start, where do we end. So for that reason, these problems tend to be a bit more advanced because they build on all the knowledge of Calculus 1 that you have, and you have to be quick and accurate. Okay, so the first problem is friendly. X equal to radical y. Well, we are not all that comfortable. We are not all that used to having our functions in terms of y. It's perfectly okay, but most of the practice you have, y is given in terms of x. So when it's given the other way, maybe a quick way of handling it is to turn this around. So if I turn it around, it becomes y is equal to x squared. So x is equal to radical y is same as saying y is equal to x squared. Of course, x here is going to be always positive because it's square root of something, so we are limiting ourselves to x's that are positive. While y is equal to x squared looks like what? Well, that is our trusty parabola. You see it over and over again. So y equal to x squared with the restriction that our x is positive. Well, how about x is equal to y over 2? Well, again, we are more comfortable with looking at this thing as y is equal to 2x. So y equal to 2x we know is a straight line with slope 2, so it's going to look something like this. So this is y equal to 2x. So what's the region that is bounded by these two? Well, if we had drawn the whole parabola here and we had drawn the rest of the this line, well, they are crisscrossing each other. When we are talking about the region, what are we talking about? It's a region bounded by these things. So we are not looking at this infinite region here, or other places. Rather, the bounded region that's between all these curves. So that is the region we are referring to. We are doing the integration on that. That's our region R. And what's our function? Our function is x squared y squared, and that would be rather complicated to draw it by hand. Let's go ahead and see if one of these software is going to help us. If my page is still active here, let's see. Okay, so in this page I can give my lower boundary, that's my x squared with the parabola we were talking about, and the upper boundary is 2x. So the region we are integrating over is this looking like a leaf or something. We are to do an integration on this thing. Our integral is some function. I had, I guess, x squared y squared over there. Here I've typed x squared y squared over 10, so that okay, the GeoGebra pages do not last that long. They kind of evaporate. Let's see if we can get another one of these pages going. Okay, now the problem is I have to type all of that stuff all over again, and it rather acts slowly. So our bottom function was x squared, and top function was 2x. You have learned in Calculus 1 how to find the intersection of these curves. You just set them equal to each other and find out the beginning and end, which we have learned is in the x direction is from 0 to 2, I guess. We are waiting for this thing to update. Okay, 0 to 2. I had a function. Now this function is a little bit friendly. It's because it's a paraboloid. So whatever function you put there, it graphs it for you, and the section of it that's above your region on the xy plane gets to be colored in blue. So here, let's see if we switch to the function that we were looking at, if we get something reasonable. So x squared y squared, at this point it's going to become about 64 or something. So for that reason I am dividing it by some number to make the picture perhaps more visible or something. Let's see if this helps. So that is just for presentation purposes. Okay, the graph of x squared y squared looks like this blue region, that the blue surface that you see here. It kind of on the sides just like a parabola, but it's like a page that is folded around the xy axis. Okay, here you see the region on the plane, that little skinny region that we had up here. That region is on the xy plane here, and what we are calculating is the volume of three-dimensional region that is built on top of this region on the xy plane, and it's below this surface. That's what we are trying to calculate. Well, the way we approach it is through iterated integrals. That is, we take it back to an iterated integral and calculate it just like how we did it last time. So the double integral becomes just the iterated integral. Let's go and see how this looks like. So now as we said last time, you have always a choice of integrating in x direction first or integrating in the y direction. Sometimes they are same amount of work, sometimes one of them is much easier than the other one. Just to have that in your mind that you have two choices. Okay, let's go after one of these choices. Suppose I want to go x direction first and then y direction next. Again, it's entirely your choice. So x direction, meaning I draw a line here at a certain y, ask myself, where do x start and where does it end? Well, how do I get that? X in terms of y is going to tell me start and stop. Which one of them is the starting one? The starting one is the straight line, which is y over 2. You want to get that right, otherwise you're going to be off by minus. Our ending place is on the parabola. That's where we are stopping, so it becomes radical y. What's the function we are integrating? Whatever is given here, f of, for example, x squared y squared. Next, well, what is its end? What's the beginning and end of y? Well, lowest point of this shape is at y equal to 0, and the highest point of it, well, you said x squared equal to 2x. X squared equal to 2x. You solve that, you get x equal to 0 and x equal to 2, and you plug it in either of these, you get y equal to 0 and y is equal to 4. So the highest point here is 4, the highest x value is a 2. So our last integral with respect to dy goes from 0 to 4. 0 to 4. Okay, for these problems, that is better than half of the problem, just to figure out where do you start and where do you stop and how do you set up your integration. Some of your homework problem is just asking you just set this thing up, and the integral itself could be a separate problem or part B of the problem or something like that. Okay, integral with respect to x of x squared, what would that be? Well, that's of course x cubed y squared, and this is divided by 3. What are my limits? My limits is from y over 2, that is x gets replaced by y over 2 and goes as far as radical y. After that's all done, we are in phase 2, which is doing the next integral, which is with respect to y. Okay, let's just go ahead and do the inner integral. Inner integral, we put radical y here, so I get radical y gets cubed, then y squared, and then over 3. And then next phase, we take x and replace it by y over 2, cube that, multiply by y squared, again divide by 3, and this whole thing, whatever it is, has to be integrated one more time. So this was a straightforward integration. Everything is polynomial, so it's not that bad. So 0 to 4. Well, it's better to convert everything to just power. So this becomes 3 halves, and 2, all told, becomes y to power of 7 halves over 3. And this becomes y cubed times y squared. That's of course y to power of 5. 2 cubed is 8 times 3, that's 24. And then all of that is dy. So by now, a problem has been reduced to a simple problem. In calculus 1, we integrate this thing. This becomes y to power of 9 halves. Yeah, of course, I have to multiply by 2/9 to compensate, and divide by 3. And then here I'll have y to power of 6, and then I have to compensate by dividing by 6, and I had a factor of 24, and all of this thing from 0 to 4. Now we have to put, so this becomes 2 over 27. This is 4 to power of 9 halves, minus this becomes 1 over 144, and 4 to power of 6. Okay, that is the answer. Well, it can be cleaned up quite a bit. So by now we are back to something like algebra 1 or something. It's just cleaning up our numbers. So WebAssign will be happy with this, as with any of the other numbers we are going to get out of cleaning this thing up. But it's up to you how much you want to clean this up. So 4 to the power of 9 halves, how do you clean that up? So this is 2 squared to the power of 9 halves. So this becomes 2 to the power of 9. And I see all base 2's here, so I go ahead, maybe 4 to the power of 6. I can write it 2 squared to the power of 6. So that I can write it 2 to the power of 12. Now to clean up, I reduce my numbers. Reducing by saying, okay, I have 2 to the power of 10 here, 2 to the power of 10 here. So let's factor it. 2 to the power of 10, this is 1 over 27th, and this is 2 to the power of 2 left, so that's going to be 4 over 144. Okay, these are all arithmetic steps. Once again, you could have stopped there, but I'm just curious how clean can we make this final answer. So this becomes 1 and 36, and then so I have 2 to the power of 10, and then between 27 and 36 I need to take a common denominator. This is an extra factor of 3 over that one, so it becomes 1 over 8, and this becomes 4, and this becomes 3. Okay, so just take a common denominator, simplify. So I have 2 to the power of 10 over 108. I can simplify both of these by a factor of 4, so it becomes 2 to the power of 8 over 27. So that's my final answer, as clean as we can make it, or 256 over 27. Okay, so we spent a lot more time on the arithmetic at the end and then at the beginning. It's typical with these problems that you are better off cleaning it up, but yeah, sometimes it's optional. Okay, let's do one more problem, and then perhaps we delegate the rest of it to other lectures. So sometimes the problem stated kind of verbally: find a volume between several surfaces. Z is equal to x squared plus y squared, x squared plus y squared equal to 4, and z equal to 0. This is a relatively simple problem, because all the surfaces are the ones we have encountered at the very beginning as the most simplest surfaces, and the difficulty of these problems is just visualizing to figure out where the surfaces are sitting and where are the intersections and so on and so forth. Okay, so let me see if I can encourage you to try to do this thing yourself. Okay, try to visualize all these 3 surfaces that we have and try to see what is that enclosed area we are trying to find the volume of. So that is the most crucial thing in this problem. So z equal to x squared plus y squared, what does that look like? What's the name of it? What does it look like? And so on. So spend a few minutes refreshing your memory on that issue. So what was that? This is, of course, a paraboloid. Kind of looks like a paraboloid that has been turning around the y-axis, the z-axis, and that is our paraboloid. So this is the paraboloid. How about the other one? X squared plus y squared equal to 4. Well, of course, in on a plane, this is a circle of radius 2. But in space, what is it? In space, of course, it is a cylinder. You remember that from beginning of a semester. So this is a cylinder. How about z equal to 0? Well, z equal to 0 is just the xy plane itself. Z equal to 0 is just the xy plane. So what is the volume we are after? We are after the following volume, the one that is sitting on top of this circle but is below that paraboloid. Well, how do we find the volume of this thing? Well, decide how you want to integrate this thing. You can go in the x direction or y direction. So what are we doing? We consider a slice of this. For say we are going to go in the x direction first. So on top of this line, we try to imagine the section of the volume we are after that is sitting right on top of that line, and then try to find the area of it. So what we do, we set up our double integral. The first one is going to go from that intersection to this intersection. So I pick a certain y, that's my y. I ask what is my start and end x. So I have x squared is equal to 4 minus y squared. So if I take a square root of this, I get plus or minus square root of 4 minus y squared. So this integral starts from minus radical 4 minus y squared to here, which is plus this is plus radical 4 minus y squared. So that's my inner integral, from minus radical 4 minus y squared to plus radical 4 minus y squared. Okay, what is the height of my surface? My height is simply x squared plus y squared. How am I integrating? I'm going in the x direction, so that's going to be dx first. Then what? Then I have to sweep my region starting from the lowest y value to the highest y value. Well, what's the lowest value we have for y? We are starting at, of course, minus 2, because this is a circle of radius 2, and the maximum value of y is plus 2. So that the volume you want to calculate will be this. Okay, so this is very similar to a problem we did last time, and I delegated to you to calculate this integral and do several more problems from this section. So these are iterated integrals. They are how we are going to do double integrals. Later on we are going to have triple integrals, and there's going to be lengthier problems of this type. Until next lecture, good luck and God bless.